Final speaker is Chong from UCLA.
Oh, yeah. Thanks for the introduction and thanks for the invitation. And I will make sure you have dinner on time. Yeah. Well, I'm in chemistry department and I will talk mostly about electrochemistry. If you know me, my previous background before COVID, my primary research efforts was electrochemistry with microorganisms, system biology, while I was considered inorganic in my inorganic chemistry in my department. So when the COVID hit, lockdown happens, and I was teaching electrochemistry. Gave me a lot of time to stare into the screen and a textbook, and then everything started. So it's relatively new. So while during COVID, I was teaching electrochemistry, and it gave me a lot of time to look these textbooks. And it just, if you read a textbook and if you think or is look at a cover of textbook, you have a common pattern that electrochemistry, when we teach students, is a lot about IV curves, right? Those traces here, they are just IV curves, a derivative of them. And when we teach students, it's about when they read it and decide what is going on, what kind of mechanisms there, and then the student make a judgment and decide on next experiment. So when I thought about what I'm really teaching, electrochemistry is really teach students like object detection and classification, right? You have IV diagrams and you teach students look at where redox is, object detection, and then based on the feature to make a classification, what kind of reaction is going on there. So that make me wonder that if the majority of electrochemistry education is about a computer vision type thing, why don't I just translate a textbook, translate what we teach students in an AI model so it can be in a closed loop pattern? So that's what I decided to do. That's some ideas that came during teaching in COVID. So, but if you think about in a broader context, earlier today in the session, we have so many fascinating talks about hardware's flow chemistry and the algorithms in a decision closed loop autonomous lab. In my opinion, that I don't have to add to any of that, but one thing I can add is data analysis. Electrochemical testing anyway is computer based, but you got IV curve. The computer, but the Bayesian optimization is not going to read IV curve by itself and make a decision. You have to translate the data you directly measure from electrochemistry into a data format that, say, Bayesian optimization can pick up and then make a decision. So that's what I thought is if I can translate IV curves, what I started teaching in the textbook, into a into a neural network here, that in an automated data analysis fashion, I can allow to finish the loop. I can let the instruments measures, they got the data, they analyze it the same way as students were taught to do in the classroom, and then they export a data format, then the Bayesian optimization will pick up. We can really close loop for electrochemical research. So that's what I thought. So with that idea, so today I mostly talk about two things before your lunch, before dinner. First is what kind of model we develop, and then I'm going to using one classic, the most common bread and butter technique called cycloptamgrams to demonstrate that what we do. And then using that, we can show you how we can put everything in a closed loop so it works. So in a grand scheme of things, I just feel like these textbooks been there for a while. Maybe we can give another way for them to exist in cyberspace, and translate textbooks into AI and a machine learning model. That's what I try to do. With that idea, during COVID, and you need the money and to pay the students, pay the bills to get things done. So I shoot an email to NSF, an eager proposal, get funded, really appreciate that, and it works well, and everything grad started. And I am, and by no means I know computer science and well, because I do electrochemistry with microbiology. So I grabbed my friend in computer science who do statistical machine learning, and my friend buddy Cyril Constantin, who happened to wrote textbooks about electrochemistry. One of the figures they show here earlier was he wrote a book. So we three of us form a team, and that's what. So what I'm going to present is the team efforts. So what we do want? Well, what I want is I want to have IV curve shown on the top left and using a neural network to change that into a mechanistic judgment. What is the mechanisms there? And I want to do it probabilistically because with finite information, all the data I have, I don't want to be very deterministic. I want to say it's probably a probability distribution across all possibilities. And with more experiment going on the fly, and that maybe the probability distribution can then converge into a single metabolism. Another question is earlier today, people talked about data and model interpretability, right? You don't want a black box. And that's the criticism sometimes my chemistry colleagues will talk about. So I really want to make sure to tell my users, future users, where the model is looking at, in addition giving an output, so that they can compare with their own interpretations. So make sure that hopefully easier for user to pick up. And also just in case things goes wrong, we know, and there's a way to check for any errors. So that's why we also, two of the output out of the model is A, probability distribution mechanism, B is a description where the model is looking at. Attentions are your need. Right, so how we get there? Well, the first thing people ask about, where do you have the training data, which I didn't talk about, it's not here for the sake of time, is electrochemistry actually is all about partial differential equations, right? It's mass transport, kinetic, boundary conditions, all of that. And the textbook does is define the initial condition, boundary conditions, the formulation of PDEs, and what means is you can use in COMSOL finite element simulations. As long as you read textbook well enough, you exhaustively sample all the parameter space defined by textbook, you got a synthetic training data of all the IV curves that include all the possibility for a certain mechanism. And and you go through one mechanism in one chapter textbook, you go next mechanism in another chapter, eventually you get a data training set that include all the variations from IV curve, and that's what we did. Once you have the training set, it's not too much different compared to computer vision. We're using the classic ResNet as a thing for our first model. In this case, it's just a classification task. There's no object detection here. We assume there's only one redox, and let the machine classify the mechanism. You see here, the first out, you have 6 for 10 grams IV curves. They would tell you what kind of probability distribution of the mechanism. And on top of that, you got a residual gradient on the last layer, and you got an attention or a proxy of where the model's attention is. And it really helps us to know, oh, yeah, the model is looking at something human does too. And that helped to convincing the users that, yeah, we are doing all right. So that's the first model, is just a classification model. The next thing is you need to add object detection. In reality, you without any a prior knowledge that you don't know how many processes are going on in your electrochemical system. So we have to let the model be able to detect each individual redox without any prior knowledge, and identify the redox features, and then classify the individual redox feature, their mechanism. So that's what we did. Took some time to change the faster RCN model and computer vision to a 1D model to tailor to the data format you would see from electrochemistry, and we made it work. You can find out the model is open source online, just online, I think 2 weeks ago, and you can find it out. So what it does, as you show, is include at least with our training set, the mechanisms that textbook dictates. And for each, the model is going to detect each redox features and each ROI, the region of interest. It will tell you the probability distribution as a vector for each mechanism. And then that really comes to the next thing is how can we incorporate it in a closed loop design? Is the vector tells you probability of mechanism within a finite amount of information. You can imagine that you can have a Bayesian optimization loop that the target is to optimize towards one of the mechanism probability by changing different conditions. They will find out and finalize the optimal reaction condition for certain transformations. So that's the goal, right? So here's one example. A little bit organic chemistry, as you have a organometallic. You have a cobalt-2 tetraphenol porphyrin, single electron quasi-reversible charge transfer to cobalt-1 anion radical. It's a nucleophile, so react with imbutyl bromide in a SN2 type substitution, and that's a classic example which talks about. We call it, and the single electron transfer is this E mechanism, is a single electron irreversible charge transfer coupled with the SN2 reaction become EC mechanism because you have chemical step after a electron transfer. Well, as we see that it's the same system, but under different experimental conditions, the voltamogram shape changes, right? So, and that image tells, as a grad student, they were taught reading the voltamogram, know what's the next experiment to do because that tells you the extent of the conversion of the second step. Well, it's the same thing if you're reading the probability distribution under 4 different mechanisms, you see that the values change. The higher value meaning that at that condition, there's a larger propensity for the reaction to go completion instead of it doesn't react. So that is will be our target in a Bayesian optimization in a loop. So that's what we do. So we decide to build it. COVID lockdown is lifted and take some time to get all the folks, computer scientists, electrochemists, and nanochemists, some my organic colleagues, and build everything in a glove box because it's for organometallic chemistry, right? And well, it's compared to what Milad showed earlier, it's just simple flow chemistry. We just build in a glove box and we try to demonstrate it is possible. We don't tell the mechanics, reaction, the system, what kind of reaction, what kind of stuff we added. We want them to figure it out by itself. So what's our goal? The goal is that I have a cobalt complex here and I just add whatever in the solution. I want to ask first question is the reaction happening or not? I'm not going to tell them, they got to figure it out self. And the second question is, if the reaction happens, what's the reaction order and what's the rate constant? I think that's the most good step. Starting for chemistry grad student, you do expect that they have that kind of capability. And I think if we want two machines to do things themselves, we want to test them too. So what we do is it's just what I said, proposed, right? You have a flow chemistry, simple, very simple in the box. They are able to change your parameters. Experimentations is going to match over 10 grams here. Is the machine learning model is going to yield the propensity distribution or probability of each mechanism, and the Bayesian optimization to read out a vector and try to optimize one of them. In this case, the second one, the EC mechanism percentage, by changing the reaction condition until they find out a reaction past a certain threshold, indicating that the reaction happens to a greater extent. And if that happens, it goes to a second step that they would further optimize the condition until you can do mechanistic kinetic analysis. Because if knowing the reaction happens is not the same as finding the condition, you can extract the kinetic information like a reaction order and rate constants. So that is why we have two-step Bayesian optimization in this case. Here's just some example, right? You can have different kind of voltamogram, each conditions. You can do a grid search. I mean, just showing the capability that just all the combinations automated and in 2,600 voltamograms and conditions, 60-hour in the box. Students were over TeamViewer. And then but what we really find is even the reaction happens, it takes much harder efforts. About only 4% of parameter space that we search are eligible for a mechanistic study to get a rate constant and the reaction rate. And so that means you need an additional Bayesian optimization to find the tiny slim slit or this part of the reaction conditions for mechanistic understandings, get a rate constant out of that. It's much harder to do, and that's why we have two layers of Bayesian optimization. But we made it. The system was tested over quite a few organic compound that my postdoc picked it up. I'm not synthetic organic chemist, so I know they exist. But it's capable to measure rate constant across several order magnitude. So because they optimize condition, the machine optimized condition by itself, and we didn't post anything. It's accurate enough that can determine a secondary kinetic isotope, basically a substituted proton to deuterium, and up to about 5% difference with a 2% relative uncertainty. So that means it's pretty accurate and it's reliable to run by itself. And it doesn't fake it, and it doesn't bluff, right? If there's no reactivity, it tells you there's no reactivity. And and this really allows to systematically compare the reactivity across different kind of substrate. Organic highlight in this case using hammer plot. Basically, my postdoc tell me that's something physical organic folks do. I learned it a year ago, indeed. But another question is, what happens if the mechanism, the reaction, there's outlier, the reaction happens, there's some unexpected scenario happens. And we accidentally, we're just lucky, accidentally find out in one case, out of no reason, the reaction happens unexpected. It does not go as the way we thought they should, but the model doesn't bluff and they tell us, oh, I don't know, there's something wrong with that, and it's come up with an error. And then if you look into the Tamgram, if you will realize that there's another alternative mechanisms through a radical pathway that instead of SN2 is SN1 type a radical pathway to finish conversion, and that give you an actual shoulder peak that lead to a warning and the program stop. So just tell you that if there's outlier, the program can detect the shoulder here and tell you something's different. With that, I do want to just show you some example that, yeah, we can, as a COVID project in the 4 years now, we are able to translate textbook, electrochemical textbook into machine learning model and analyze for Tamgrams to bridge the data you measure to the data you need for a decision-making process in electrochemical research. And we can demonstrate that as a proof of concept in molecular electrochemistry. And thank you. I really appreciate NSF because I have no background on this, and it's really an eager project that started everything, and my collaborators too. Thank you for your attention, and happy to answer questions.